So today in the second lecture of the chapter Newton's laws of motion, let us discuss the basic forces that we study in this particular chapter. The forces that usually act on bodies that we study in this chapter and their properties, how they act, how we use them into questions when we solve questions depending upon various situations with us. So these are 5 forces, basic forces that we are going to study. One is the gravitational force, the other one is normal reaction, then tension, then spring force, and finally we will study friction as a force. So we will do them one by one. Before we start with these forces one by one, let us just look at one distinction that we have in all of these forces. Out of all these forces, it is only the gravitational force which can act from a distance. When the two bodies that are exerting gravitational force on each other, they may not be in contact with each other. They can exert a force from a distance on each other, and such forces, I hope you all know, are called non-contact forces. And another name that we give to them is field forces. Field forces. Why do we call them field forces? Is because these forces and the way they exert a force on the body, that can be explained on the basis of the field that they create around us. You might have heard of the term gravitational field, which is nothing but the space that a mass creates around it, and when another mass is brought in that field, it can experience that force, right? So we explain the nature of these forces or the way they act through the field that they create, and hence such forces are also called field forces. On the other hand, all the other 4 forces that we are going to discuss are all contact forces, because they require a physical contact between the two bodies which are exerting force on each other, right? So these are 2 basic types of forces that we study: the field forces or the non-contact forces, and the contact forces. I hope you have understood the distinction well. Now let us discuss each of these forces one by one, starting with the gravitational force. So gravitational force, as we all know, is the force that acts between any 2 masses, right? Let's assume there are masses m1 and m2 which are separated by a distance r. The important thing here is the separation that we take is between their centers here. If you don't know this, understand this now. The r value that we take in the formula for gravitational force is the center to center distance between the 2 bodies. And we know that the force is given by the Newton's law of gravitation, F is equal to g m1 m2 by r squared. Now in this particular chapter, which gravitational force are we going to study? We are going to study the gravitational force that a body which is kept either on the surface of the earth or near to the surface of the earth experiences due to the earth. So we are basically working on the earth system. We are observing bodies moving on the earth or near to the earth. So for us, one of these 2 masses would be the earth. And as we understand that earth is a big object, I'll just take a part of the earth which looks like a curved surface, and let's say there is a body which is kept over here, right? Now instead of these 2 masses m1 and m2, our one mass will be the earth itself, which will have a mass me, and the body which is kept over its surface, let's say, has a mass small m. Now when we try to find out the center to center distance between the body and the earth, do you all understand that since the body is very small in comparison to the earth as a system, if this is, let's say, the center of the earth, can we say this distance that we are supposed to take as the center to center distance between the bodies, can we say this will be nearly equal to the radius of the earth itself, right? Because the size of this body will be very small in comparison to the size of the earth. And in that case, when we try to write the gravitational force that this body experiences towards the center of the earth, yes, this is the nature of gravitational force. It always is an attractive force and act between the centers. So one body pulls the other body towards its center with this force, which is now for the earth mass system given by F is equal to g. The first mass is the earth itself, the mass of the earth, times the mass m, divided by the distance between them, the center to center distance, square of that. So re squared, the radius of the earth whole squared. Okay, so this is the expression that we get when we are discussing the gravitational force acting on a body kept on the surface of the earth. Now see carefully that in this expression, G, the universal gravitational constant, that is a constant value throughout. Mass of the earth is a constant, isn't it? And the radius of the earth is also a constant. So we understand that this whole term here is a constant and we can easily find out its value. So when this value was calculated, it was found to be equal to, approximately equal to 9.8 meter per second squared. Yes, this was an acceleration that we got, and we call this value of acceleration due to gravity as small g. And while we replace this constant with small g, the force expression will become m times g. So it is from here that we get the weight of a body or the gravitational force on the body acting when the body is kept on the surface of the earth. Understand that the weight or the force of gravity acting on the body would still be the same if the body is taken to a small height above the surface. Let's say the body is kept here, somewhat above, a little above the earth's surface, at a height h, let us say, such that the height h is very small in comparison to the radius of the earth. Do we understand? In that case also, we can say that the force between the body and the earth will still remain the same, because the distance between the body and the earth's center will not appreciably change in that case also, isn't it? So in this case also, we say that the gravitational force on the body and hence the acceleration due to gravity g, they remain the same. It does not appreciably change. So the force of gravity will still remain mg. Understand that this force of gravity will always act towards the center of the earth. So it will always be vertically downward if the earth's surface is below the body, right? So if we have to show how this force acts in the usual cases, we can take up an example here maybe. Let's say there is a surface like this. There is a tabletop and there is a block of mass m which is kept over this table. Can we say, because the earth's surface will be beneath this surface, the gravitational force that this block will experience will be given by mg in the downward direction, right? On the other hand, if you have the same block kept over an inclined surface, a surface which is now inclined, and let's say you may know the angle of inclination as well, this angle is theta, and there is this block which is kept over here over at this inclined plane. Understand the block would be kept like this now, but in this case also, if the block has a mass m, do we understand that the gravitational pull acting on it will still be vertically downward, right? Because the earth's surface will be like this and it will be pulling the block towards its center. So the force will go down, vertically down always. So the gravitational force is always vertically downward for bodies which are kept on the surface of the earth. The only special case or a special condition that you can take here would be when you take the earth as a small system. Let's say like this, if you are able to show the whole of the earth as a sphere that you can see here, this is the center of the earth. Now understand that in this case, if the body is kept over here, right here at the top, then the gravitational force on the body will be like this, mg downward. Whereas if the same body is taken at some other latitude, let's say of the earth, then the same gravitational force will act like this. But generally in this particular chapter, we don't consider such cases because we are dealing with small objects which are kept on the earth's surface, and the earth's surface is considered to be very large in comparison to that body. Okay, so this change in the direction of mg does not come here, at least in this particular chapter. So this is gravitational force. Understand that the value of g is going to remain constant if we are taking the body kept on the surface or near to the surface of the earth. Okay. Now we come to the next force. The next force that we are going to study is called the normal reaction. It is called normal reaction, or sometimes we simply call it the reaction force, or sometimes simply the normal force. Okay. Now what is this force? Let's understand this. So to understand, let us take up an example. We have a surface, horizontal surface, and there is a block of mass m kept over the surface. The surface is, by the way, rigid. It is a solid surface. Now do you understand that the block, because it has a mass, it will be pulled down by the gravity with a force of mg downward, right? Now if the block is free to move, we understand that the block will start moving under the effect of gravity in the downward direction. But as a common observation, we observe that such blocks will just stay there on the table. So let's say this block is like a book which is kept on a table. As we see the book, even though it has a mass and it is being acted upon by the gravitational force, it does not go down, it does not move down towards the Earth's center. Why so? Because it is kept on a rigid surface, a solid rigid surface, which does not allow it to move down. Now, in the previous lecture, we studied this fact that when a body is in a state of rest or of uniform motion and it maintains that state, it does not change that state, that means that the net force acting on this body must be 0, right? From that argument, can we say that on this block also there must be at least one more force acting on it, which is completely balancing or cancelling the force of mg, due to which the net force on the block is 0 and because of which the block is staying at rest, it's not moving, right? What is that force and where is it coming from? So understand that in this case, as the block tends to move down under the effect of gravity, a force comes from this rigid solid surface and acts on the block right in the opposite direction, so that it just balances the weight, the force of gravity acting on the block. Why is this force coming and acting? It is coming simply because the block otherwise will have a tendency to move down, and since the surface on which the block is kept is a rigid surface, it cannot allow it to move down, right? So just to prevent its downward motion, this force comes and acts in the opposite direction to where this force is acting mg. Now this force, it has a certain nature. Because this surface on which the block is kept is horizontal, this force that comes and acts on the block from the surface will be absolutely perpendicular to the surface, and that is why we name it normal force. Okay, so the term normal is coming because this force N always acts perpendicular to the surface from which it is coming. So it's coming from this surface, the surface will exert a force always perpendicular to it. This is one basic property of the force of normal reaction. The second thing is, why are we calling it a reaction force? Understand that in the last video we talked about the concept of action and reaction forces, right? So action force here in this particular case is the force of gravity which first comes and acts on the block, due to which the block had a tendency to move down. And to balance that, then a reaction force comes from the surface on which the block is kept and acts in the opposite direction to the force of gravity. So in that sense, this normal force is actually a reaction to the force of gravity that came and acted on the block first, right? That's why we call it the normal reaction. Normal because it's always perpendicular to the surface that exerts the force, and second, a reaction because it's actually a reaction to a certain action force which has already come up. Okay, so this is the basic nature. I hope you all understand that since this surface is always acting perpendicular to the surface that is exerting the force, in case I tilt this surface slightly, let's say the same block is now made to sit on an inclined plane like this. There is a block of mass m, let's say, and do we understand that in this case, if at all a normal force acts, which it will, because there is a force of gravity still acting on the block, pulling it down to not to balance it this time the normal reaction cannot balance it, but if we try to see what is the nature of normal reaction, this time since the surface of the incline is at an angle theta, the normal force that will come and act on the block will act perpendicular to the inclined surface like this. See that the normal force always acts away from the surface also. So it's not acting like this ever, it's always away from the surface. Okay, so this is another thing that you can keep in mind. So this is the way in which the normal force will act on this block when the block is kept on an inclined surface. The important aspect here for the normal force is that since this normal force is not acting exactly opposite to the direction of mg, it will not be able to balance the force of mg. At least it will not be able to balance it completely, right? It will only be able to balance a component of mg only. For example, I think we discussed this in the previous class also, or maybe we can discuss it once again. If you look at this figure carefully, this force mg can be resolved into its two components. One component of mg we can take along the incline, which will be by dropping a perpendicular from the mg force like this, and the other component of mg we can get perpendicular to the direction of the incline, which will be like this. If you look at the geometry of the figure carefully, if this angle is theta here, we can easily see that if I draw a line over here, this angle would be 90 minus theta. And this angle is the same as this angle here. See it carefully. These two are the same angles. So this angle will also be 90 minus theta. And then in that case, we can see that this angle comes out to be theta once again. Why? Because this direction and this direction both are perpendicular to each other, so the total angle that they make should be 90. So if this angle is 90 minus theta, this has to be theta, right? So it is from here that we understand that this angle, the angle that the force mg makes with the direction perpendicular to the incline, is theta. And as soon as we get that, we understand that the component of mg in this direction will be mg cos theta. This is coming from vectors. We are resolving our force mg in two mutually perpendicular directions. The component of mg perpendicular to the incline is mg cos theta, and from there we understand that the other component along the incline, the component of mg will be mg sin theta. This is one very important thing that we use very often in the chapter, because we get a lot of such questions which are based upon inclines. So this particular part must be very, very clear to you. How do we get these components of mg? How always for an incline making an angle of inclination theta, the component of mg along the incline always comes out to be mg sin theta, and perpendicular to the incline it's always mg cos theta. You can check that for yourself once with this figure. Okay. Now the next thing is, instead of mg now we can represent its components. Mg sin theta and mg cos theta are now together representing the force mg, and in this case practically how do we see the block to be moving? Because now the net force on the block will not be 0, because normal reaction cannot completely cancel out mg. Do we expect the block to move? How will it move? It will tend to slip down along the incline, slide on the incline, isn't it? So whenever it moves, it will move like this. So whatever acceleration it will have in the direction of the incline or along the incline, which also means that perpendicular to the incline, the acceleration of the block will be 0. I hope you all recall the same thing we discussed in the previous video also, when I discussed with you what all steps do we take to solve questions based upon the Newton's laws, and there we talked about this aspect that we need to be able to identify the direction of acceleration of the system, and then we can consider the acceleration perpendicular to that direction to be 0. Why do we do that? Because we say that if acceleration along this direction is 0, the net force along this direction must also be 0. So perpendicular to the incline, the net force acting on the block must also be 0. And for that, when we try to write the equations, now I can remove the force of mg here because it is represented by its two components. So what do I do now? I say next that perpendicular to the incline, since the acceleration is 0, the net force must be 0, which means that the net upward force perpendicular to the incline n must be equal to the net downward force, which in this case is mg cos theta. So we have already started applying the Newton's laws that we studied in the previous lecture here in this particular topic. So as we discuss forces one by one, maybe we will discuss how we use the Newton's laws in these cases as well, and that will make us more confident in the topic right from the starting. So this will become our equation of Newton's first law, you can say, because here we are taking the net force is equal to 0, or it is a special case of second law also, F is equal to ma, where a is 0, right? Both of them will give us the same expression. From there we get the value of normal reaction coming and acting on the block. Now before discussing the value of normal reaction over here, I could have discussed with you the value of normal reaction here itself. Do you see that in the first case, where the block was simply kept at rest, normal reaction was able to balance mg, could we have simply written n is equal to mg? Because the two forces are completely cancelling out each other, their magnitudes must be the same, right? So in the first case, normal reaction was actually equal to the force of gravity. But in the second case, what we are getting is that the normal reaction is just equal to the component of gravity. Now it's only mg cos theta. On the other hand, along the incline, if these are the only two forces acting on the block, there is no other force here, then can we say this force mg sin theta still remains on the block? And it is this force now that will create an acceleration in the block. So we say that parallel to the incline or along the incline, now we can write the equation that helps us find out the acceleration of the block. What do we do here? We use the Newton's second law. Why second law? Because we know that along the incline there is an acceleration. So we use net force is equal to mass into acceleration along the incline. And how do we use that? F net, the net force on the block along the incline, is mg sin theta, and that is equal to the mass of the block times its acceleration along the incline. You see here that from this equation we are easily able to get the value of a as g sin theta, which is the usual acceleration of a block which is slipping down an incline if there are no other forces acting on the block other than the force of gravity and the force of normal reaction coming from the incline. So this exercise that we have done just now is a very basic exercise in the chapter. This makes you understand how you resolve forces, how you write the force equations along two mutually perpendicular directions, the basis of which we studied in the previous lecture where I told you all the steps to be taken, right? So this is one very important application of that, a very basic and an important application. Okay, so through this we understand the nature of normal reaction force. How does the force of normal reaction act? It always acts perpendicular to the surface and it always acts away from the surface. These are the two major things. Let us take up a few more examples or situations where we try to find out the normal reaction acting on bodies. So let's say we have a case here where there is a floor and there is a wall attached to it like this. A floor and a wall, and we have a ladder, let us say a ladder or a stick which is just standing like this, taking support from the wall as well as the floor together like this. So this is the stick that we have. Now except for all the other forces, if we try to look at the normal reaction forces that are acting on the stick, understand that at all points of contact, normal reaction is generally available there at all points of contact. So here in this case, understand that the rod is in contact with two surfaces here. One is the floor at this point and the other one is the wall at this point. Both these surfaces then will exert a force of normal reaction on the rod. And how will they exert the forces? The floor will exert a force of normal reaction perpendicular to itself. So like this, perpendicular to the floor itself, call it N1, the first normal reaction coming and acting on the rod. And the second normal reaction that the wall will exert will be perpendicular to the wall itself and away from the wall, so call it N2. So this is how this rod will experience the two normal reactions acting on the rod from the floor as well as from the wall. So this is how normal reaction acts in this case. Another case could be, what if we try to find out the normal reaction that's coming and acting from a curved surface? Let's say this is a curved surface and there is a body which is kept over this curved surface. Let's say there is this block which is just kept over the curved surface like this, and we want to find out the direction of normal reaction. What we do in such cases is, we first draw a tangent at the point of contact of the surface. So this is a tangent that I have drawn right at this place, at this particular place where the block is just in contact with the curved surface. And then what we do is, we draw a perpendicular to that tangent like this, and this perpendicular direction is actually the direction of normal reaction. Okay, so there will be many cases where we shall get to see curved surfaces creating normal reaction on bodies kept over them. This is how you take the direction of normal reaction there. Let's take up another example based upon the same concept. Let's say there are two balls, let's say, which are kept right in contact with each other like this, and let's say they are being held within some rigid container like a box like this, and there is a third ball which is kept right over these two balls like this, so that this ball is just in contact with the two balls. Now, if I name these balls, let's say this is ball 1, this is ball 2, and this is the ball 3. If I try to find out the force of normal reaction that the balls exert on each other, or let's say the force that the balls 1 and 2 exert on the ball 3, how do we find out those forces? Okay. So, what do we do here is we first draw a tangent at the point of contact between the first two balls, and we say that in this case the normal reaction will be perpendicular to this tangent. So, this will be the direction of normal reaction which the ball 3 will, the ball 1 will exert on the ball 3, because it is towards the ball 3 and away from the ball 1. So, this surface is exerting a force on ball 3 in this direction. Let us call it N1, the normal reaction coming from the ball 1 on the ball 2. Okay. Let me write it over here, N1. This force is exerting this surface is exerting this normal reaction. Similarly, can we also find out the force that the ball 2 exerts on the ball 3 by once again drawing a tangent first at the point of contact and then drawing a normal to that, perpendicular to that? Call it N2, the force that the ball 2 exerts on the ball 3. As you look at these two forces, you will observe that both of these forces will tend to pass through the center of this ball. Why is that so? Do we know this basic property of a circle, that the radius of the circle, which starts from the center and goes till any point on the circumference, it is always perpendicular to the tangent drawn at that point where the radius touches the circle. These two are always perpendicular to each other, right? So, it is perpendicular to the tangent, the radius, and we know that the radius always passes through the center. So, these directions of normal reactions N1 and N2 in this case are essentially going along the radial direction on the ball. So, this is another case where we see how normal reaction acts, right? So, having understood the basic nature of normal reaction, you see that normal reaction is a reaction force that comes as a result of some other force that's already acting. I hope you understand that in this case also, it is because of the weight of the ball 3 that it will try to press the balls 1 and 2, due to which the normal reaction will come and act on the ball 3 from balls 1 and 2. Also understand that in this case, the same forces N1 and N2 will be exerted by ball 3 on ball 1 and 2 respectively. Where is this coming from? This is coming from the Newton's third law. Action and reaction are equal and opposite. So, if ball 1 exerts a force N1 on the ball 3, the ball 3 will exert the same force N1 on ball 1 in the opposite direction, right? And the same goes with ball 2 and 3 also. The force N2 will be exerted upon by both the balls on each other in opposite directions. Yes. So, the next force now that we can discuss after this would be the force of tension. Let's discuss tension now. So, what is tension? It is not the mental tension that we are going to discuss here. This tension is the tension created in a string or a rope or a thread like system. So, let's say we have a string like this, okay, and initially when the string is simply hanging just like that, it will be a relaxed loose string. But let's say we connect a block just beneath it, the string, at the end of the string like this. Now, do you understand, because of the block connected with the lowest part of the string will become tight. It is this tightening of the string which we explain on the basis of a force that comes and acts within the, in between the molecules of the string, that we call as the force of tension. So, how does it come and how does it act? Let us discuss both of those. Do you understand that as we hang this block of mass m beneath the string, due to the force of mg, the force of gravity, this block will have a tendency to move down. But since it is still at rest, can we say it is the force that the string is exerting on the block, due to which the block stays at rest, right? So this, what is this, where is this force coming from? It is coming from the string and acting right here at the point where the string is connected with the block. So where is this force coming from now? We say that in the process of the tightening of the string, what happens is the different particles of the string, the particles of which the string is made up of, they kind of feel a stretch within, they kind of move slightly away from each other, not very much but very slightly away, negligibly small distance away from each other, due to which they start pulling each other towards themselves. Why does that happen? If we go into the molecular details of structures, we know that there is a certain equilibrium distance between any two molecules, right, when it is inside its material, in its lattice. So if x is the equilibrium distance, x equilibrium is the equilibrium distance between these two particles, whether you take these two particles closer to each other or you take them away from each other, in both the cases they will try to come back to the same equilibrium distance, right? And in order to do that, whatever way the force they have to apply on each other, they do that. So for example, if you bring these particles closer to each other, they don't want to come closer, they want to retain their equilibrium the equilibrium distance between them, and for that then they start pushing each other away from each other. So they say that they start repelling each other if you bring them closer from their equilibrium separation. Whereas if you take them slightly away from their equilibrium separation, now they will start pulling each other towards, so that they can once again come to their equilibrium separation. So this is the basic nature of all intermolecular forces. Okay, so the same thing happens here in the string. As the string becomes tight, stretched kind of, it does not increase in its length because that change in distance is very small, negligibly small. What happens is all the molecules start pulling the very consecutive molecule towards themselves. So for example, if we take any one of these molecules of this string, let's consider this molecule. Let's say this molecule will pull this molecule towards itself, the one which is just above it, and it will also pull the molecule just below it towards itself. So both the molecules are being pulled towards it. Same thing will happen with this molecule. This molecule will pull this molecule towards itself and the upper molecule also towards itself. So they are all like in a kind of tension, kind of stretched system, right? And since this thing happens everywhere, each molecule experiences this, understand that the lowest molecule that is there, which is just tied to the block M, it will pull the molecule just above it in the downward direction, whereas there is no other molecule beneath it. So what it does, it creates the same pulling force towards this block in the upward direction. And it is this upward pulling force that the last molecule of the string creates on the block in the upward direction, that we call as the force of tension. In fact, this force will be the same throughout. Everywhere, each molecule will be pull its consecutive molecules both above and below with a force of tension, the force T. Okay. Same thing happens with the topmost molecule of the string. The top molecule of the string will be pulling the lower molecule towards itself, and above it there is the ceiling or the support through which it is connected. So it will pull that support also downward. Fine. So this is the nature of tension force. To simplify it for the cases where we are supposed to study it, we simply say that if there is a string which is connected to a block of mass m, then the string will pull the block upwards with a force of tension T. And if the block, under the effect of this tension as well as its gravitational force mg, if the block remains at rest, we can say that by Newton's first law, T should be equal to mg. The net upward force acting on the block should be equal to the net downward force. Okay. Now, when I say that the tension in the string remains the same throughout, everywhere the tension is T, this is valid only under a certain condition, and the condition is that the string must be massless. Okay, so this is an important point that we all must understand. T is same or constant throughout the string if the string is massless, which seems to be a little idealized situation. It is an idealized situation. Right now we are discussing only ideal systems where we can keep assumptions to simplify the mathematics of the questions. Okay, so that's why we say that the string is kept massless, and when it is considered massless, we can say that the tension throughout the length of the string would be the same. If the string has its own mass, then we have to deal with the mass of the string also at every point as we move over the length of the string. We have to deal with the mass of the string also. That becomes a little more complex, though it can be handled easily. For now, since we are just starting with things, maybe let's keep things simple, and maybe let's discuss all the strings to be massless, which is generally given to be the case in the questions also. Okay. So once we have understood how the force of tension acts, so let's just revise this once. Tension comes through strings or ropes or threads, one thing. Second thing, tension is always towards the string, because the last point or the last particle of the string which is connected with the body, it pulls that body towards itself. So it's always away from the body towards the string, the force of tension. Okay, this is an important property. The same tension that the string exerts on the block in the upward direction, it exerts on the top of the ceiling, like there at the top support, in the downward direction. So the same T acts here also. And then by the Newton's third law, we can also say that the ceiling will also pull the string with the same force T upward. Here the block will also pull the string downward with the same force T, right? So all these aspects we can now discuss one along with the other. The same thing we can discuss if we have let's say horizontal string. So for example, if we have a block of mass m which is connected through a string or a thread somewhere, and let's say this string is massless, it does not have any mass, so that the tension throughout the length of the string is going to remain constant, and let's say we pull this string with a force F towards right. Now if we are pulling this string with a force F, do you all understand this pulling force F will be the force that will that is coming and acting on this very first particle of the string? So it is with the same force that the other particle which is just next to this first particle should be pulling this particle with, like the same force should act in the backward direction also, so that the net force on this particle is 0. Now this is one important aspect, let us discuss this as well. When we say that the string is massless, it has a mass which is 0. What is special about zero mass systems is that zero mass systems can never have a net force acting on them. Why so? Because F net, when you write mass into acceleration, even if they are moving with a certain acceleration, because their mass is 0, their net force should always be 0. Okay. So in this particular case, even if the block moves with a certain acceleration towards right, and with that the whole string moves with an acceleration A towards right, still the net force acting on every particle of the string should always be 0, because it has no mass, the mass is 0. Which makes us understand that this force that we exert at the starting point of the string, that force itself becomes the tension in the string, T. T becomes the same as F, because everywhere each of the particle of the string then will be pulling each other with the same force F to keep the net force on the whole string to be 0. Okay, on each particle the net force should be 0. So this is an important point here, that when a massless string is being pulled with a certain force F, that force itself becomes the tension of the string. Okay. Then we can have cases like this as well. Let's say we have a mass m1 and there is another mass m2 which is connected to m1 with a string, and now let's say m2 is being pulled towards right with a force F. Okay. So see that there would be one string over here and another string over here. Two different strings can have two different tensions. Generally they will have two different tensions. So if we assume here that let's say this string has a tension T1 and this string has a tension T2. Because the string with tension T2 is directly being pulled with a force F, we understand that T2 will simply be F. So the force acting on M2 over this point, at this point itself, will be F, right? Whereas if the tension T1 is the tension in the second string, the one that connects M1 and M2, this tension will act on both the blocks in certain directions. Let us see what that direction is. Do we understand that on M1, the tension T1 will act away from the block M1 and towards the string? So it will be like this. T1 will act towards right on the block M1. Whereas on M2, the same tension T1 will act in the backward direction. Why so? Because the same string will be pulling M2 towards itself. Towards itself means like this. From on M1 the force will be towards right, on M2 the force due to the string will be towards left. This is coming from the same string, and this is coming from the same basics that we understood here. The same string that pulls the block M upward, it pulls the ceiling downward with the same force T, right? So the same thing is happening here also. So this aspect is important to understand. We can take the same set of two blocks suspended through vertical strings also. So let's say there is one first string that's holding a mass M1, and then another string that holds a mass M2 which is connected to M1. Okay, and let us say the question is that we are supposed to find out the tension in both the strings. Let's say we consider the tension in the first string to be T1 and the other string to be T2, and then we try to see how we get the values of T1 and T2 when we know the mass is M1 and M2. Okay, this particular question we can do using our basic steps that we discussed in the previous lecture of identifying the system, writing the forces, identifying the forces, drawing the free body diagrams, and then writing the equations. Okay, like that we can do this. So before we start off, let us look at a few things carefully. If we assume that T1 is the tension in the upper string, can we say that T1 will act on M1 in the upward direction like this, and the same T1 will act on the ceiling in the downward direction like this, right? Whereas the tension T2 in the second string will act on M2 in the upward direction like this, whereas on M1 the same tension T2 will act in the downward direction, isn't it so? So this is how the tension forces are acting on both the blocks. But on these blocks there is not just tension which is acting, their own weights are also acting, right? What are the weights? The weight of M2 will be M2G acting downward, whereas the weight of M1 will be M1G acting downwards. So now since the situation looks a little complex, let us draw the free body diagrams of both the blocks and get the forces on them clearly in a clear picture, and then we shall write the equation. So that makes a question easily solvable. So let us first take up the block M2, because M2 is hanging beneath and it has less number of forces acting on it. We shall first discuss M2 and then we shall discuss M1. So first of all, on the block M2, do we see that the forces acting on the block M2 here are M2G downwards, the weight of the block M2, and the tension T2 acting upward, right, coming from the string. Do we all see that these are the only two forces acting on the block M2? There is no other force on M2. Now since M2 is at rest under the effect of these two forces, can we say that the two forces must be balancing each other? They must cancel out each other completely, which means that the upward tension force must be equal to the downward gravitational force. And this is the equation that we get, and this gives us the value of T2 right away, isn't it? So by writing the force equation along the vertical on the block M2, we are directly getting the value of T2, the tension in the lower string. Now let's do something similar in the block M1. First we'll draw the free body diagram. So on M1 there are more than two forces. If you look at it carefully, on M1 there is a force of gravity, which is M1G. Then the force of tension T1 acting upward from the upper string. And look at this carefully, there is a force T2 also acting on M1 but in the downward direction. Yes, this force, because the lower string will be pulling M1 towards itself, the upper string will be pulling M1 towards itself. So this is how the two tensions act on M1. And now once again, since the block M1 is at rest, not moving anywhere, we can use the Newton's first law and say that the net upward force T1 should be equal to the net downward force T2 plus M1G. T2 plus M1G is the net downward force which balances the net upward force, isn't it? Now, the value of T2 is already known to us, so we can substitute it here. T1 will then become M2G plus M1G, right? So, that T1 is M1 plus M2 times G. So, this way, by drawing the free body diagrams and by identifying the forces that are acting on the system and then using the force equations from Newton's laws, we can solve for any unknown force. Here T1 and T2 are the two unknown forces, isn't it? So, this is the basic nature of tension force. I have just taken a few very simple examples to make you comfortable with the way the tension force acts. The next force that we are going to discuss is the spring force. Spring force now. Spring force is a little complex. Why so? Because we will see as we discuss the spring force is not a constant force. Its value changes at every moment. In the previous all the cases that we have discussed, the gravitational force, the normal reaction and the tension, we have seen that once we have obtained the value remains constant, it does not change, but that is not the case with the spring. So, let us say what happens with a spring. What is a spring? As we all know, a spring is a system which looks like this, isn't it? The basic entities attached with a spring are its natural length, which is the length at which you will generally find a spring to be kept. It does not, and at this length, there is no force acting on the string, it is simply kept just like that. And it is also not exerting any force anywhere. Okay, so this L0 is called the natural length of the spring. Natural length means the length at which the spring generally wants to stay without any force. Then there is something that we call as the value K, which is called the spring constant. We shall see what the spring constant is very soon. This spring constant is a constant that depends upon the material of the spring and its length and such things. So, it is essentially a constant value for a given spring. It does not change as the spring opens up or compresses, it remains the same, but for different strings it can take different values. Okay. So, understand that a spring will have its own, any spring will have its own natural length and it will have its own spring constant. Fine. Now, what we do now is, we take the spring, we connect it with a block, let us say, and we pull this block by exerting a force in any direction towards right, for example. In the process, do we understand that the spring will open up, right? When the spring opens up, it will look like this. Let us say the block has reached here in some time, so that the block has undergone a displacement of x in the presence of the external force that was acting on it. And do we understand that as the block shifts by a distance x towards right, the spring also opens up by a distance x? We say that the spring undergoes an elongation of x, or it stretches by x. Now, the nature of spring is such that it always wants to remain in its natural length, and for doing so, as you stretch it, it will create a backward restoring force. We call it restoring force because it tries to restore the original length of the spring. We call it the restoring force or the spring force, which is found to be directly proportional to the extension that you have created in the spring. The spring force is directly proportional to x, and when you try to remove the proportionality constant, you get K times x as the spring force or the restoring force. Not just that, look carefully that as the block is displaced towards right, this restoring spring force comes and acts towards left. So, direction wise, the spring force is just opposite to the direction of displacement x, right? So, this equation then becomes the defining equation for a spring force, the restoring force created by a spring. What does it say? It says that the spring force acting on a spring which is stretched by an amount x is given by kx, and the direction of the restoring spring force acts opposite to the direction of the stretching. So, if the string has been stretched towards right, the restoring force will be towards left and vice versa. Okay. This is also true when a spring is compressed. So if the original spring, which was like this, okay, with a natural length L0, if you compress it, let's say someone creates a force at this point itself, some force which compresses the spring, and the spring after a while looks like this, its end has come here. So the end of the spring has undergone a displacement, leftward displacement of x. We shall see this also means that the spring has got compressed by x. So in order to restore its natural length L0, the spring will create a restoring force in the opposite direction, and it will be given by the same expression. The force due to the spring will be minus of k times x. Here the minus sign is telling you about the direction of the spring force, which is opposite to the direction of x, and this is the magnitude kx. Okay. So generally, if we understand the direction of the spring force, we simply write spring force F spring is kx itself. So in questions, if we don't have to deal with the direction part, if we just have to write the magnitude, we just write the spring force as kx itself. Okay. So now this is the basic nature of spring force. Now how do we use it into questions? Let us see that. Let us take up a few examples now. If I take this spring which is having a spring constant of k and hold it vertically like this, and then I attach a block of mass m with it. Do you understand that because of the weight of the block, once again, because the gravitational force will be pulling this block down, the block will tend to move down, and as it moves down, it will stretch the spring. Unless it moves down, the spring will not exert any force on it, right? The spring will simply be in its natural length, so no force coming from the spring. But as soon as you stretch the spring will start exerting a force, and as the block goes further down, the stretching in the spring also increases and the force of the spring also keeps on increasing, till you reach a certain point where the spring has stretched by a certain amount, due to which it can now balance the weight of the block. So the mg force with which the block is being pulled down by the gravity, the spring force is just able to balance it, and let us say in that process the spring has got stretched by a distance x naught. We call it the equilibrium extension of the spring. Like this, it has gone down by x naught, let's say. Do we understand from this figure that x naught will also be the extension in the spring in this process? So how much restoring force in the upward direction will the spring create? It will be k times x naught, and this force will be directly acting on the block because the spring is directly connected with the block. Mind you that the same force kx naught the spring will be exerting right here at the top also, but since the top point is at rest, it cannot move, we are not discussing that. Right now, if we just discuss the forces acting on the block, the forces acting on the block will be two, kx naught the spring force acting upward, and mg the gravitational force acting downward. Under the effect of these two forces, if the block stays at rest, can we say the upward kx naught should be equal to the downward mg, right? And from this expression we can find out the equilibrium extension created within the spring when a block of mass m is connected to it beneath it, right? So this is how we can get this expression just by balancing the forces. See that we have used the Newton's first law over here, kx naught is equal to mg, right? Net upward force is equal to net downward force. So this is the basic nature of spring force. Understand that spring force is slightly more complex because it is a direct function of x which keeps on changing. As the block continues to move towards right, the spring force keeps on increasing, right? And the direction also we have to take care of. So these are the four basic forces that we have discussed in this video: the gravitational force, the normal reaction, the tension, and the spring force. We shall see how we use them into questions. And the fifth force, the force of friction, that we shall be discussing separately in a separate lecture, because the frictional force is a slightly more elaborate force. In fact, we shall see when we discuss friction that there are basically two types of frictional forces. So that we shall do in the next video now. In the next class, we shall discuss the force of friction, and then we shall see how we use all these forces together into questions. So if you are liking the video, if you find it beneficial, please like it, share it with your friends, and do subscribe to the channel. and do let me know if you want me to take up any certain specific topic here. Thank you.